what are numbers? Well, what are numbers? Well, here to tell us all about it is Toni, and we might have a special guest appearance today as well.
Okay, so what are numbers? Well, the ducks there are because the theme is we're going to get our ducks in a row. I mean, we all know what numbers are, don't we? Do we?
Well, I think so. we know them from a very young age, don't we?
We're going to talk about what children learn about numbers from when they start school, and then we're going to go touch a little bit. It's going to be very informally on what people learn about numbers in university, and then the research, the current research that is happening. And so you're in for a few surprises. And so I'm going to say thank you to Mike Pearson for the ducks. And I'm just wondering if this expression ducks in a row is used in other languages. Maybe it's just very English. I don't know.
I don't know it in any other language, but I haven't heard it, but it could be.
So there are many different answers given to the question. And in over centuries, people argued about this question. Negative and fractional and even irrational numbers were accepted by scholars in Europe in the 16th century and earlier in some older civilizations in other parts of the world. But strangely, until the 19th century, scholars were arguing about negative numbers and complex numbers. And these numbers were often scornfully referred to as absurd numbers and imaginary numbers. However, they're very much the stuff of mathematics, even school mathematics today. So we talk about the question in a very informal way. We'll discuss different sets of numbers, including four-dimensional numbers called quaternions and Clifford algebras. So we're going to start with counting numbers, and then as we meet each new set of numbers, each one will be bigger than the set will be bigger than the one before it, and including the ones we already knew about.
So each set will encompass the earlier numbers that we're going to talk about. Okay.
Now, Caroline and I have often talked about how little children learn to count. It's interesting, isn't it, Caroline?
It's a game. It's lovely. I mean, even from when they're babies, counting steps, taking them up the stairs, and then before they able to talk properly, they like the rhythm. They'll say, "Oh, da 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 da," just when you're counting steps or you're following on, when you're doing things that you count with them. And then you've got the joy of actually counting things, and the game, of course, of counting just random number counting before they know how to count properly. They want to count, they've not necessarily got it, so they'll go 1, 3, 2, 7, but they love the process, even if they haven't quite got it yet.
But when they can count, and they know they can do it, and they can count up to 100, they're very proud of it, aren't they, Caroline?
Oh, yes. So I can count this high, and I can count this high.
And then they realise that there's no point in going on higher.
The little mathematical brains kick in, and they develop. Well, that might be. Do you think that's possibly the first actual mathematical thinking that kicks in, where they think, wait a minute, there's a better way of doing this, or a more efficient way of doing it.
Well, they really think it goes on forever. It's as simple as that. So there's no point in me going on and on and on, because this counting business goes on forever. And they have then an awareness of the concept of infinity. They haven't actually done anything much, but they haven't met a number system, but they already have this understanding, this intuitive understanding of infinity. And so roughly speaking, a number system is it's a closed set of entities that can be combined by the operations of addition, subtraction, multiplication, and division. And closed means that all the answers produced are still numbers. Let's think a bit more than that. So,
okay, so you combine numbers, you put numbers in, you get numbers out. And
exactly.
That's, yeah.
Yeah. And these are just the familiar operations of adding, subtracting, multiplying, and dividing. So quite early in school, children learn to write the correct number in the box to make that correct. So they would write 3 in the box. Now, even before they start school, they know a little bit about adding. I mean, just when it's talking about the size of a collection of numbers. So they have 3 sweets and somebody gives them 2 sweets and they've now got 5.
Even if they literally count all the sweets, you might count
yes.
3 sweets and count 2 sweets, and then you might have to actually count all the 5 sweets. They might not be able to make that connection yet, but they're very happy to do it.
Yeah, but they get to the point where it's seen as being very easy.
Yeah.
And if they've got 10 sweets and they divide it with another child, then they'll each get 5. And they know a little bit about adding in that practical way, and they will get it right because it matters. So before they start school, I'm not talking about 3-year-olds, I'm talking about 4 or 5-year-olds. And once they begin combining the numbers, they're going beyond the numbers just being counting and into the realm of the number systems and arithmetic. So they're understanding numbers as more than just labels for naming and recording the size of collections of objects. They think of these numbers as entities that can be combined themselves according to agreed rules, which we call arithmetic. So if they count sweets, it is just the same process as counting coins or counting their toys or whatever. So the same numbers apply, and they can combine the numbers in these simple ways. So the more we know about and use this arithmetic, the more we appreciate that it's useful. It provides a tool for solving human problems of all sorts. So maths is really useful and number work is useful. So when we can do that, what next? Can we undo that process? We have 5, we add 3, we get 8. Can we undo that process? Subtraction. It's a natural idea based on concrete experience, not of increasing the size of a collection of objects by combining 2 collections, but reducing the size by removing some of the objects. So if I've got 8
eggs and you eat 3, you don't have 8 eggs anymore. You've got 3
and
less.
if I have 8, let's say I've got 8 pounds, okay, and I give you 3 pounds, then I've only got 5 pounds left. We use numbers to describe the size of collections of objects, and we need a number for the set that's nothing in it, because, well, if I have 8 pounds and I give you 8 pounds, then I've got nothing left. And we need to expand our concept of number to include the number 0. So that's what you will put in the box. 5 minus 5 equals what? That's
0.
a number.
Yeah.
And while the use of numbers, including place value, dates back at least 5,000 years, scholars in Europe were still debating whether 0 could be a number even 500 years ago. So in other parts of the world, in India, for example, 0 was known as a number and it was used as a number, whereas here, well, relatively recently, it wasn't. People didn't really understand 0 as a number. Now, once you've got that far, and then particularly up here in the winter, and with modern refrigerators and freezers, even small children are quite used to sub-zero temperatures. So if we ask what number do we add to 13 to make 9? What would you put in that box, Caroline?
Well, yeah, you'd have to have -4.
But
so now we've got, but we don't have a negative numbers yet. We haven't worked that out. So
yeah, but it's fine. What we're saying really is that as we proceed through school, our children learn about more numbers that they didn't know existed before.
Right.
So they're going to learn about -4 as a temperature in the freezer, and they make a snowman. That snowman was made by the children who live next door to me, okay, with their father, and they know that that food it would go rotten if you didn't keep it in the fridge or the freezer. So this has a real meaning. These negative numbers have a real meaning. We can't say there's no such answer to a subtraction like 9 minus 13 once we know about negative numbers. And they've got many uses, as we've been saying. So one of the things we do is we put them on a number line. So there's a number line marked, and there's with the arrows at both ends mean it goes forever and ever in both directions. But I've only labeled it from -10 to +14. But I've indicated there the 13 and the 9, and you can see that you go in the negative direction from right to left, 4 steps to go from 13 to 9. So this is what we call a negative number, is what we call a directed number or a vector. And that's again got the idea of a directed number or a vector has a lot of uses. For example, in physics and in engineering, a force is a vector, because a force has not only got a magnitude, but it is applied in a certain direction. And of course, it's not just backwards and forwards along a line, it's in any direction. So the number 4 then is called the inverse, -4 rather, is called the inverse of 4. And in fact, 4 is the inverse of -4 because you add them to get 0.
Right.
So that is an idea of an inverse process. It's getting back to where you started with. And every integer has an inverse. So if you go the same distance in the opposite direction, you get back to 0. The number added to its inverse gives you 0. So now this is another number system, and we're using the rules of arithmetic of adding integers now. Now then, another way to look at this is with a little bit of symbolism. So now I haven't written down the empty box. I've written this unknown x. We don't know the value of x, so we just write down x. But if we do know a and b, then we can find x by saying x is b minus a. And that's just expressing in a different way what we had on an earlier slide. And for all equations to have solutions, we need to be working with integers, not just positive numbers. So for example, 9 plus x equals 5 has no solution at all. We're talking about counting numbers only, but it has the solution x is -4 or -4 in the set of integers. And also, maybe before children meet negative numbers, they also meet fractions, which mathematicians call rational numbers. So just as horizons are extended to include negative numbers, everyone learns that fractions are also numbers. And mathematicians, as I say, call these rational numbers. Children are, as we said earlier, they're interested in fair shares even before they start school. So division is also based on concrete experience. And a rational number like 2/3. 2 over 3 is 2 divided by 3. It means you've got 2 whole things and you divide the 2 whole things into 3 equal parts. So addition and subtraction are inverse operations, we have just said. Similarly, multiplication and division are inverse operations in the sense that 5 times 4 is 20. And if we want to get back to 5, we divide 20 by 4. So they're inverse operations. And it's not until we work with rational numbers that every addition, subtraction, multiplication, and division of 2 numbers in the set gives an answer that's also in the set. Because if, for example, you haven't got rational numbers and you have 5 divided by 2, fraction 5 over 2, which is 2.5. If you don't know about rational numbers, you don't include it. It's outside the set you're talking about. But if we want all the numbers to be in this closed system, then self-contained system, then we're going to be talking about not just negative numbers, but also fractions. Rational numbers. So here's a picture.
Decimals. I mean, we're not talking about just integers anymore either.
No, you can express the same number as a decimal.
Yeah.
And as you say, that's really important to note. It's just one of the conveniences, I suppose, of using mathematics, that you can write the number either as a fraction or a decimal or even a percentage. If you're saying it's a percentage of something. Mm-hmm. So here's a pretty picture. So this is a picture of what we've been doing. We have natural numbers first, with then 0, and counting numbers with 0, natural numbers. Then we expand our ideas to include negative numbers. So we've got integers and rational numbers, which include integers, because we can have a rational number 6 over 1, that's rational. Mm-hmm. All the points on the number line. So no, not all the points if we've only got rational numbers. We'll come on to that. Mm. So here we've got a fraction. Sorry, here we've got an equation again. AX equals B. And we can't solve it. We can't solve 2x equals 5 if we don't know about rational numbers.
Right.
But once we've got rational numbers, we can solve that. So with a, b, and x rational, and we can solve all such equations. So now what we're going to now have is a formal way of writing down what we've just been talking about. But in primary school, the children will learn all this by the time, and they'll be very used to doing it by the time they're 9 or 10 years old. So first of all, now look at those. They're a bit scary, those words, if you insist that anybody should learn all the right words, but those are the words used by mathematicians. But what are we saying about addition? Well, it's closed. The set of rational numbers is closed. We've talked about rational numbers. And now what does associative mean? It means if you've got 3 numbers, you can add them in any order. But this isn't true for subtraction. What do you think about the thought bubble there, Caroline?
Yeah, the thought bubble it's not. You can't reverse them in the same way at all, because when you're taking them away,
7 minus
when you're just
5,
adding them, you can add any order, but when you're subtracting, the order matters.
Yeah, but 7 minus 5 is 2 on the left, and 2 minus 2 is 0.
Yeah.
So on the left of that expression for subtraction, you've got 0, and that's not equal to what you get on the right.
No, on the right you get, because 5 minus 2 is 3, and then it's 7 minus 3 is 4. So yes. 0 is not equal to 4.
Yeah. So we have to be clear what we mean by this word associative. But I think now it's obvious to even small children that this is something that happens in arithmetic that they know about. Now, we talked about the additive identity, which is 0. When you when you add 0 to a number, you don't change anything because you're adding nothing.
Right. So the identity of a subtraction or addition is 0.
0. And every number has an additive inverse. And when you combine any number by adding or subtracting with its inverse, you get 0. And this is an example of a mathematical system called a commutative group. We'll talk about commutative in a minute. Now, that's addition. Okay, so it's the mathematician's words, but it's very simple rules. Multiplication is just as simple. So if we leave out 0, multiplication is associative, just as we found addition was associative. And the rational number 1 is the identity. 1 times anything is that same thing if you just multiply by 1. And every rational number has an inverse. Now note that 0 doesn't have a multiplicative inverse. That's why we leave out. We can't divide by 0. Okay, so we leave that one out. And addition and multiplication are commutative. What it means is if you add two numbers, you can add a plus b, or you can have them the other way around, b plus a. Right. And you can do the same, a minus b, and that is equal to b. A times b, rather, is equal to b times a for all a, b.
And we assume that subtraction is not commutative because it's not even associative. What about division?
Well, 8 divided by 4? 2. And 4 divided by 8?
Right. Half.
They're not equal. That's a half.
Yeah. So that's a nice way of doing it, to figure out whether or not they are commutative or associative is do an example.
Yes, yes. Because you are whereas if you're going to prove something is true, you've got to prove it for the infinitely many cases. But if you're going to prove something is false, you only have to find one counterexample.
Yeah.
Okay. So we've got now multiplication is another commutative group. Now I slipped the word group in there. This is what the mathematicians call it, a system which works like we've described, and where these rules are obeyed is called a group. And we've got an additive group and a multiplicative group when we're working in the set of rational numbers. Okay. Now, if we combine in our calculation some adding and some multiplying, then we've got this distributive law. So if we multiply 3 times 4 plus 5, that's 3 9s are 27. And that is the same as saying 3 4s are 12, and adding 3 times 5, which is 15. And for any numbers, I've just given you an example there, but it always works. It always holds. There is this way of combining multiplication and addition works. It's what we mean using the brackets there. We often say, well, we do what's in the brackets first, but that's just writing down the fact that this is distributive. So when you put two groups together like this, and they sort of interact with each other in this way, you call it a field. Not where grass grows and you have cows out there.
So no cowbells here then?
No.
No daisies and no cowbells.
This is what mathematicians call a field. Why they decided to give it that name, don't ask me. Don't ask me.
I wonder if it's because there's an electronic magnetic field. I wonder if it's
Well, that's a good idea. I have no idea. I'll try and find out. So we're going to move on though, because we're going to meet a new sort of number. Well, it's not new. The Greeks 2,000 and more years ago knew that root 2 was
new to this
irrational.
presentation.
It's approximately 1.414, but it can't be given exactly however many decimal places we use. However, we don't really need it except as a theory. I mean, in practical, everyday measuring, we don't need it. Of course we need it. We need that precision in when we work things out. It will make a difference if we get, more decimal places there in our calculation. But if we're measuring a length, then we can approximate that length. We can get very, very close, good degree of accuracy, by just taking a ruler and measuring it with a rational number. So practically speaking, for everyday measurements and engineering purposes, we don't need that precision, but we do need it in calculations, because when we're multiplying up then it will make a difference to get that accuracy. So now we've got what mathematicians call real numbers. So in the dark green band there, we have got the numbers that are not rational, the ones we've just been talking about, the irrational numbers. But then when we're talking about real numbers, it includes everything that we've been talking about earlier. And none of this is new to the primary school child.
Right.
Now, what they often use in primary school is this number line, which we talked about before. Well, you're teaching at the moment. Have you got a number line on your wall, Caroline?
Not in the classroom. Yes, yeah.
So,
mine's going vertically at the moment because we're using the temperature as the analogy. So we're using the thermometer
right.
version.
So each real number corresponds to exactly 1 point on the line, and all the points on that line are represented by real numbers. So we call this line the real line. I mean, in primary school, they call it the number line, but mathematicians call it the real line.
I didn't know that. If I had heard it, I didn't remember it.
The real numbers are equivalent to one-dimensional vectors. So we mentioned vectors earlier, but we mentioned them in relation to integers. But actually, real numbers are one-dimensional vectors. And together with
and
addition,
they don't have to be integers.
No, they can be anything. But so every single point on that line, every point, not just the ones I've marked, but every point corresponds to a real number. And any real number, however large or small, any real number has its own point, its own position on the real line. So these real numbers actually work in much the same way as we were talking about the rationals in terms of combining them with the arithmetic. So in the field of real numbers, we can solve equations like x squared equals a, right? But only when a is positive. For example, x squared equals 2 has two solutions. X is negative root 2 and x is positive root 2. And we've talked about root 2. But x squared equals a doesn't have any real solutions when a is negative. In other words, we're saying we can't take the square root of a negative number. Well, we can't as long as we stay with real numbers. But
we're going back to those absurd numbers now.
Complex numbers. Oh, well, yes, they would call all sorts of names. But they have been recognized as appropriate numbers, useful numbers, and they're two-dimensional. So it's not just a number line and points on a line. complex numbers correspond to points in two-dimensional space.
So on a plane, not just
that's
on a
right.
line, it's also on a, this now we're talking about on a plane.
Yeah. Yes. And equations like x squared equals a, and you know, equations that involve x squared and some x terms and some numbers, these are called quadratic equations. So in order to solve all quadratic equations, we need to be working with complex numbers. Now, the very simplest equation that is like this, that's involving complex numbers, is x squared equals -1. And we have a very happy little number, very useful little number, that's the solution to x squared equals -1. Now, this was at the turn of the century, between the 18th and 19th century, that Gauss, he proved and published this fundamental theorem of algebra. And that is, every polynomial equation, as long as you're working with complex numbers, has a full set of complex solutions. And at that time, then, complex numbers were accepted as proper numbers. Now, what that theorem means is that every quadratic equation has got 2 solutions, every cubic 3 solutions, and so on. So that's Gauss's fundamental theorem of algebra. So what else can we do with complex numbers? Now, as we just said, they correspond, they're two-dimensional, and whereas real numbers correspond to points on a line, complex numbers correspond to points in the plane.
Okay. Okay, so they're vectors as well, presumably.
Yes, and they're vectors which, like forces, can go in any direction. Now, we can, because every point in the plane represents a complex number, one of the ways of talking about it and, you know, saying what it is just to give the coordinates of that point, the x and y coordinates.
Okay.
But to do the algebra with it, with complex numbers, we write it in the form x plus yi. Now, that actually means that to go to the point xy, you start at the origin, okay, and you go a distance x across in the positive x direction, and then you go a distance 1 unit up in the y direction. So the complex number I has a length 1 unit, and it is a direction straight up. So you can see that if you go x units across and y units up, you get to the point xy. So that makes sense to use that notation, x plus yi, for the point with coordinates xy. So let's look at this mysterious I, which is still referred to as an imaginary number, although it's very much widely used in physics and engineering, and it's electrical engineering particularly, all sorts of engineering, and it's a very useful little number. So what role does it play in numbers is what we're doing at the moment. So now, if you were not thinking of I as anything special, and you had that example, you would add the 7 and the 2 to get 9, and you'd add the 6i and the 4i to get 10i. And that's exactly how the arithmetic, the addition of complex numbers works. And also, if these were 2 forces, it's the way you add the 2 vectors. Or to any 2 vectors, it's the way you add the vectors. Now, the subtraction here, again, same sort of rule applies. if I now take what I have on the right-hand side, the 9 plus 10i, and you subtract one of those numbers on the left, 2 plus 4i, I get 9 minus 2 is 7, and 10i minus 4i is 6i. So I get the other number that appeared on the other side at the top, above. So you can see how just as with when we're working with real numbers, addition and subtraction, the inverse processes, the subtraction undoes the addition. But it's a very natural algebra here. It's easy. There's nothing new to learn there, really. But there's something slightly new when we come to multiplication, because I squared is -1. So does that make sense to you, Caroline, when you look at how that's worked out?
Yeah. You had me up till I squared equals -1.
Ah, well, that's the definition of I squared.
Okay.
We're going to be exploring it in some detail now, and it will make perfect sense in a minute. So we've got 7 times 2 is 14, and 6i times 4i is 24i squared, and 7 times 4i is 28i, and 6i times 2 is 12i. So we can easily add the 28i and the 12i to get 40i. And since I've let you into this big secret, wasn't a secret anyway, that I squared is -1, we've now got 14 minus 24, so we get -10 plus 40i. Now, just as addition and subtraction are inverse operations, multiplication and division are inverse operations. So if I take that number on the right, the -10 plus 40i, and divide it by the number, one of the numbers on the left, I will get the other number on the left. And so there it is written down. The -10 plus 40i divided by 2 plus 4i will give me my 7 plus 6i. That is the process of division, the operation of division being the inverse of multiplication. So there you have a simple algebraic system, and with I squared equals -1, the complex numbers can be added, subtracted, multiplied, and divided with the same rules as elementary arithmetic, so that the complex numbers form a field.
That's it. Again, I think I said it last week as well, that it's just amazing what people have actually discovered over the years. This is all research and thinking, and it's over the different centuries as well. It's fascinating.
And what is so important to recognize is that modern physics and engineering would be impossible if you didn't have these complex numbers. So they're not just some pure mathematics that mathematicians, amuse themselves with. They're really practical, a practical number system. So we now have 3 fields of numbers: the complex numbers, the real numbers, and the rationals. So we've talked about them, and we've realized that we knew about all these things, but we didn't know these in school anyway. The children don't know these mathematical names.
Yeah.
Now, here there's something else that's absolutely beautiful about this little number I. So I've drawn you a little sketch there with the point 50 and 05 on it. And now you've got to think about the vector from the origin to the point 50 and rotating that vector by 90 degrees. So a rotation by 90 degrees, or a quarter turn, maps the point 50 to the point 05. Okay.
Right. Yeah.
Right. Now then, let's look at why I said that I was going to do something rather clever here. So the 0.5 plus 0 times I is that point which has coordinates 5, 0. And if I multiply that by I, then you just apply the algebra we've been looking at. We've got 5i, but I times naught, that just all is naught. So there's no real part to that. Okay, we have just got the point with coordinates 0, 5 now. So just by multiplying, using the algebra that we've just been talking about, the vector that goes from 0, the origin to 5, 0, and rotating it by 90 degrees, just by multiplying by I, it does that. It does exactly that.
It's very, yeah, it's again, whoever worked that out must have been so tickled pink.
Yes, I mean, that's the joy of mathematics, is that there's so many pretty little results like this, and important and useful results. So a quarter turn about the origin is equivalent to multiplying by I, and 2 quarter turns make a half term. So another quarter turn moves the 0.50 to the point minus 50 equivalently. Okay, this time we're multiplying by I squared, and we're changing the sign. So we're going from plus 5 to minus 5.
Okay.
And this is again sort of tying in with the fact that we had I squared equals minus 1. So a half turn, that's 2 quarter turns, is equivalent to multiplying by I twice, which must be the same as multiplying by minus 1.
Yeah.
All this works beautifully. It's a little complex number corresponding to the point 0, 1, the complex plane, not only allows polynomial equations to have solutions, but gives a powerful tool for working with rotations. So here we have the diagram, and I've made this diagram go a bit further. If one-dimensional real numbers can be generalized to two-dimensional complex numbers, both systems form fields, the obvious question is, what about higher dimensional numbers? Now, here's where we start to think about the history. And you've been in Ireland on this day when they all celebrate this discovery of quaternions, haven't you, Caroline?
Yes, I think it's his birthday that they actually celebrate. That they celebrate his birthday by doing a tour of not just that bridge. There's several bridges, and so if you're in Ireland, in Dublin, on the 16th of October, you can actually get a guided tour. I'm sure you can do it at other times of the year as well, but there's a particular celebration on his birthday on the 16th of October every year. Even last year, halfway through lockdown, that still happened. It was just done virtually. The people were there, but they were filming it rather than having live visitors.
Well, the story goes that he was walking with his family, his wife and family, on a Sunday afternoon along the river, and probably ignoring the family and thinking his own thoughts
doing his
about
mathematics.
Yes, and the light bulb simply flashed in his mind, and he realized that this search he'd had for a long time about higher dimensional numbers, what the answer was that there are no three-dimensional numbers at all, but he was the first person to identify and describe the quaternions, which are four-dimensional numbers. And much of vector algebra is based on using quaternions, simple equations for reflections and rotations in three-dimensional space. And
don't worry, we're not going to actually do that maths here. We're just telling you
no,
about
we're not.
it.
But
Yeah,
Einstein,
you said it's geometry as well. It's algebra and so no. It was the two things that are interchangeable.
yes, yes, indeed.
It was the algebra in the geometry, and the geometry in the algebra. Was that it?
Indeed. And the other thing that quaternions are used in is Einstein's four-dimensional space-time, because they're four-dimensional numbers. Now, Alan's going to come and join us. We're talking about history of discovery of these numbers, and so come and say hello, Alan.
Let me just introduce you a little bit, because Toni was saying, oh, well, this is the field that Alan works on. Hello, Alan. This is Alan Beardon.
Toni and Caroline have asked me to say a few words about
Sorry, Toni, can you ask him to start again, because I interrupted him.
Mr. Caroline.
Sorry, Alan. Sorry, I was introducing you, so I'm just going to absolutely say nothing now. You just talk. But please start again.
Go
on. So what I'd like to do is to try and give you some indication as to how geometry fits in with numbers. So first, let me.
Yes.
So first, let me give you the briefest potted history of geometry you'll ever get. Euclid and the other Greek geometers studied plane geometry and really introduced the subject of plane geometry about 2,000 years ago. In the late 1600s, Newton introduced the study of calculus and planetary motion. Now, he studied the motion of planets, and that involves obviously the geometry of three dimensions, the way the planets are moving around the sun and so on. And in the late 1900s, Einstein said that we're living in space-time, which is three space dimensions and one time dimension. So that's four dimensions.
Can we go back, Alan, to these Clifford algebras? I thought you might say a bit about Clifford algebras here.
I'll come to that in a minute.
Okay.
There are physicists today who actually believe that we live in 11-dimensional space, but we're not going to go down that route today. But what I want to do is to take you back to some of the history of the way these ideas developed. And I want to do this by looking at three mathematicians of long ago and tell you about their views. First, I want to mention Thomas Hobbes, who lived in roughly 1600 onwards. And he was somebody who was a philosopher and an amateur mathematician. And indeed, he didn't actually take up mathematics until he was about 40 years of age. And he loved geometry. To him, mathematics was geometry. He was against all abstraction, all abstract ideas. And in fact, he described a book published at that time in algebra as something in which the symbols disfigured the page and made it look as though there'd been a chicken scratching around on the page. So he was a pure geometer and against algebraic abstraction. On the other side of the coin was René Descartes. Descartes was a great philosopher. He was very interested in education in general, in the way in which the mind worked, how people thought about things, how people learned about things. And Descartes' great contribution to mathematics was that he who introduced coordinates into geometry. We call the coordinates Cartesian coordinates in honor of Descartes. And Descartes' idea was that if we can describe the geometry of the plane in algebraic terms, we can then use the algebra, as you've seen earlier today, as a tool to prove theorems in geometry. So Descartes was concerned really with using algebra as a tool to solve geometrical problems. It's a slight understatement, but that's roughly the idea. If we fast forward about 150 years or so, we get to Felix Klein, a German mathematician, who gave us what I think, and what many people would say, is one of the most profound ideas of all mathematics. Klein actually said that group theory, and you've learned about groups earlier today, group theory and geometry are actually the same thing, but described in a different language. So if you think about geometry, even in its simplest terms, say geometry of the plane, you have such things as translations, rotations, you can flip triangles over, turn them upside down, and so on. These are the sort of rigid motions of the geometry, and geometry is built on this idea. And group theory actually is exactly what you need to describe these motions. In a sense, you can think of group theory as the bookkeeping of the physical geometry. In the other direction, if you start off with group theory, then it turns out, and we're not going to follow this now, turns out that you can build a geometry out of the group theory, and the geometry you get is precisely what the group theory said you would get. So these two things are really just different perspectives of the same single mathematical object. This is an extremely deep idea, and it permeates through all of mathematics now. Of course, you've seen today that numbers lead to groups. So the implication of Klein's idea is that numbers have an impact on geometry. And indeed, the types of geometry you get are very much bound up with the numbers, whether they be rationals, irrationals, reals, complex, quaternions, and so on. All of these different number systems provide you with some group theory, which, according to Klein, will provide you with a certain type of geometry. There's a quotation from Klein that I'd like to mention, that he said that regarding the fundamental investigations of mathematics, there is no final ending and no first beginning. And what he means by this is that you have never solved a problem. In fact, Descartes said that if you solve a problem, you merely open, these are not exactly Descartes' words, but it's effectively the same. If you solve a problem, that means you merely open the door to another problem. And what Klein is saying when he says there is no first beginning is that wherever you are in mathematics, you can always look more deeply at where you came from, at what the rules of the game are, and you can keep on going back and you can keep on going forward. So let me just conclude this very brief description with a sense of what mathematics really is about. Mathematics is about taking ideas and examining them carefully, challenging them, trying them out on examples, discussing them over centuries, in fact, over thousands of years in the case of geometry, until we really understand in a very deep level what is happening and why it is happening. And when, as a community, we've reached that stage, we have to develop a language which properly expresses those ideas and can show us the beauty and the power of the ideas. So mathematics is, among other things, a very precise language for giving clear descriptions of deep ideas. So the ideas of groups of rational numbers and subquaternions and so on that you've heard are not something that we've pulled out of a hat. They're something that have resulted as a process of evolution over thousands of years to turn out to be the right language for the deep ideas. I hope that helps. Thank you.
So
Thank
can
you.
we just talk about Clifford algebras, Alan? Because we skipped that because you joined us, and we were just about to talk about Clifford algebras because we've been expanding our ideas of numbers. We got to quaternions, well, sort of, a little bit about quaternions, but then so we didn't just stop there. Mankind didn't just stop there. So Clifford algebras were named after William Clifford, and they generalized complex numbers and quaternions. And what he discovered was that you can have many systems of numbers, but dimensions are only 2, 4, 8, 16, dimensions that are powers of 2, no other dimensions. For example, there's no number system of 3 dimensions. Now, addition works in all dimensions, but multiplication does not always. And so some of the properties of a field are lost. For example, quaternions are not commutative under multiplication. But Clifford algebras are important, aren't they, Alan? Can you just say a little bit about Clifford algebras? Do you want to? They're important in a variety of applications.
Well, for example, Clifford algebras are, if you like, is the algebra of 4 dimensions is a Clifford algebra, and this tallies with Einstein's view that we live in a 4-dimensional universe, 3 space and 1 time. The real issue about 2, 4, 8, 16 and so on is that those numbers turn out to be the dimensions that are required to have a, shall I say, satisfactory multiplication. Addition, it presents no problems in all dimension. If you think of a motion, a translation, it's obvious that you can translate 1 dimension, 2 dimensions, 3 dimensions. And if you think about it, I mean, it's not difficult to see that you can make translations in all dimensions. And translations are really the shifting, the addition of something. So the translations correspond the geometric notion of translation corresponds to the algebraic notion of addition. And that works perfectly fine in all dimensions. It's when you come to multiply things that things get more difficult. The rules for multiplication present much more problems, many more problems than the rules for addition. And it turns out, and I mean, the reasons are deep and they're mathematical and they're found in number systems, but you can only get a sort of satisfactory notion of multiplication in these dimensions. But even so, the multiplication in dimension 2 is very, very special. It commutes. For complex numbers, the product of 2 complex numbers is independent of the order in which you take them. That means they're commutative. But in 4, 8, 16 and so on dimensions, they're not commutative. So you lose some of the power when you get to 4 dimensions. When you get to 8 dimensions, you lose a little of what you had in 4 dimensions. But I think I'm right in saying that from 8 onwards, they all stay, the multiplication looks the same. So 2 is very, very special, dimension 2. Dimension 4 is special, and dimensions 8 and 16 and so on are not so special and weaker, that you can do less at those levels. But the real fact is that you can only get an even halfway satisfactory definition of multiplication when the dimension is a power of 2. And that actually ultimately comes out of the arithmetic.
Yes, it's we've been talking about the big picture now, haven't we? And it's ranged, without getting too technical, from kindergarten mathematics to the fringe of research into analysis and applications of numbers. Now, There is a wealth of literature to take the reader further at every level. And we've got some links which will give you a simple way to, here are the links, to start if you want to explore a bit further. So NRICH and Plus are two magazines which some of you may know, and you may like to, if you haven't met them before, to explore some of these articles. And there are other websites.
Those links are all in the description.
Perfect, perfect. Now, Caroline and I and many more people are working to provide all these resources as unpaid volunteers, and they're freely available to everyone. AIMSEC supports and empowers teachers in really seriously deprived communities in Africa. Now, Alan and I know this place because it's a short walk from where we have been living. So we live in a very nice flat, very comfortable, but close to us in Fishhook, people live in this district, and those are the conditions. And that isn't a picture taken a long time ago. That's a picture taken 3 or 4 years ago. Now, what we're aiming to do in AIMSEC is to give children a better education so that when they grow up, they can get better jobs and a chance to escape poverty, to make a better life for themselves and to make a contribution to their communities. So if you can afford to, please make a donation to support the work of AIMSEC, whatever you can afford. Just a small amount we'd be very grateful for it. So it's time to say goodbye from Alan, from me, and from Caroline. It's the end of this Happy Maths Hour. Bye, everybody.
Thank you. Goodbye.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest